So our next speaker is Harry Hong-Yun Zhou from MIT. He's going to talk about ultra high rate QEC code based on the previous speaker's construction on reconfigurable atom array.
Okay, great. Yeah, it's great to be here. Lots of familiar faces and friends. Thanks for the invitation. So today I'll be following up on the nice talk by Kenta earlier and talking about how these ideas of constructing codes with very high rates can actually be brought into a practical domain, both in terms of the regime when we think about circuit level simulations and their performance, as well as when we think about the implementation on specific hardware systems. Here I'll be mostly talking about its implementation in reconfigurable atom array systems, but the same ideas I'm sure can also be applied to many other settings like trapped ions or other ones. Okay, so, and I should also mention that this is joint work with Chen, Casey, Andy, and Nishad, collaboration between a couple of different institutions. So as I'm sure everyone is very familiar with here, combating errors is one of the core challenges as we think about large-scale quantum computing. If we look at the physical error rates that we have today on the order of 10 to the minus 2, 10 to the minus 3, and compare that against what many of these large-scale quantum algorithms seem to require, we see a very large gap, which we widely believe necessitates quantum error correction to bridge this gap. However, despite the need for this, this still remains one of the major bottlenecks when we think about the resources we need. For example, if you look at the state-of-the-art algorithms used for factoring, say, 2048-bit RSA, one of the standard applications that a lot of people like to look at, the actual algorithmic qubits is on the order of maybe 1,000 or so. Whereas when you take these and compile them into a concrete QEC implementation, as, for example, was done in this paper by Craig, this ends up being around 1 million or so qubits. And so you see that there's a very large overhead, in this case in space, but also in time in many cases, from trying to have a quantum error-corrected implementation. And so this motivates the development of methods to reduce this overhead. And we've seen a lot of great work across the field, many of which are represented at this workshop, where we started from this surface code regime where we're taking, say, 1,000 or so physical qubits to encode one logical qubit. There were these lines of work maybe 3 or 4 years ago, starting to venture into a regime where we're now using higher rate codes, such as the bivariate bicycle codes, or simultaneous to this BB code or gross code paper from IBM, we also had results on hypergraph product codes and lifted product codes, where now you maybe take 1,000 physical qubits and you encode tens of logical qubits. And so in today's talk, I'll be talking about some of the recent lines of work that really try to push this even further, where instead of talking about something that is still high rate, but maybe not quite getting close to order 1 or unity rate, we're really trying to push things into a regime where the constant factors are also quite good. And just to have a mental model, you're looking at maybe 1,000 physical qubits encoding on the order of 500 logical qubits. So it's really a much higher rate. And what I'll be showing you is that quantum memories in these settings can actually get to this regime of around 2 physical qubits per logical qubit on average, while approaching the utility scale logical error rates at these block lengths that are maybe 1,000 or so, which I would argue are like reasonable if we think about the types of system sizes that we would want for these eventual applications. This talk will mostly focus on memory, but we'll be hearing from Maddie later on about complementary work that also tries to think about what an architecture would look like as we think about these large-scale computations. Okay. So I'll start with telling you a little bit about how these codes are constructed, in large part a review of Kenta's previous talk. I'll then tell you about how, as we think about a hardware realization, what considerations would come in. And we'll see that a lot of the structures that we tend to see for these quantum codes, such as these ideas of taking lifts, thinking about cyclic structures, very naturally make it suitable for a hardware-efficient implementation. Then I'll move on to circuit-level simulations, where one of the crucial ingredients is a hierarchical decoder that allows us to access much better logical error rates than one would naively have. And finally, I'll talk a little bit about the Pareto frontier of designing and constructing these codes. So quantum low-density parity check codes, in which you have error-correcting codes with sparse parity check matrices, are very widely used nowadays, both in classical and quantum coding theory. On the classical side, if you look at the protocols that power our modern communication systems like 5G, you can go online and kind of read the technical specifications. You find that many of them are indeed based on classical LDPC codes. And if you just look at the tables that you find there, you typically find rates with a mother code of maybe a rate of 1/3 or so. Many of the concrete instances go 1/2. You sometimes even see numbers as high as something like 95%, depending on the noise levels and whatnot. They also often come with fast belief propagation-based decoding algorithms, which give them very good performance in practice. So on the quantum side, there's also been many interesting ideas in this regime. As was mentioned in the previous talk, one of the new constraints is that now the X and Z checks need to commute. And so there are additional structural conditions that must be satisfied in order for it to be a valid quantum LDPC code. From an implementation perspective, in addition to the ease of decoding, which was, I think, the main motivation for considering LDPC codes on the classical side, on the quantum side, we also have additional reasons why this is nice. Having a low weight parity check means that it's a lot easier to implement. And so we can very effectively limit error propagation, which in turn improves the fault tolerance when we think about a concrete implementation. Now, if we look at the constructions as of maybe last year, you'll see a lot of nice constructions in various regimes. I think the most exciting constructions at the time were these constructions that had a block length of around 100 to 200 physical qubits. And you typically see rates that are around 1/10 or so. For example, for the gross code, you have 144/1212. So that's a distance of 12 and an encoding rate of 1/12. So it's pretty good, fairly good parameters. If you increase the distance a bit to 18 or so, believed to be necessary in that case to reach, say, a teraquark type footprint, then you're looking at an encoding rate that is 1/24 or 5% or so. Okay, so it's a natural question to ask, can we do better than that? What types of regimes should we be thinking about as we try to push these parameters from something that is maybe a few percent to something where the constant factors are really a lot better? And as we think about building what I'm referring to here as ultra-high rate quantum LDPC codes, so something that really is getting to like 30, 50%, where the constant factors are also really good. This is just a very vague, I'm using it in a hand-wavy way, but just to distinguish from these earlier constructions that are maybe sub 10%. I think one of the key things is that now, in order to get this very high rate, so if we think about the gross code, right, you actually have an overcomplete set of checks. And so really the logical operators that you have come from redundancies in the system. But to get to something that is really order 1 rate with very good constants, getting an extensive amount of redundancies to cut down carve out the logical subspace starts to become hard. And so you really want to directly structurally build in these logical operators. In the classical case, such structural ways of doing it can be obtained by shortening, which is just deleting rows of the parity check matrix so that you encode more information bits. But this is hard to do in the quantum case. for two reasons. The first one is that you need the X and Z checks to commute. And so as Kenta mentioned, if you just naively do this deletion, then after you do delete, the original rows become logical operators. And so that has a pretty strong bound on the distance, on the number of logical representatives that you get, which is undesirable. I guess the second one is what I just mentioned, and you also need the structure so that they commute. So we have these two types of obstructions that we need to get around. Kenta had this very beautiful insight that you can actually design things in a way such that the rows you're deleting have a different structure from the rows that you're keeping, so that you still maintain orthogonality through the construction while being able to not have these low-weight things that you deleted be logicals. So more specifically, in his construction, you take these block cyclic structures which give you enough structure at the protograph level to design things. You then plug in affine permutation matrices, which in general can be non-commuting, but you can also design them to be commuting, right? Like a cyclic permutation is just setting A equals 1 here, so it's a special case. And so you have quite a lot of structure to both have some non-commutation, which prevents the deleted rows from becoming logicals, while having enough structure to have commutation between the parts that you do want to be commuting to satisfy CSS orthogonality. This row deletion increases the rate, so you can get something that by design already has something close to rate 1/2. This use of affine permutation matrices makes it a lot easier to satisfy the non-commuting things that prevents you from having a low-weight logical operator. One can also design the screening in a way that gives you relatively good girth, and you can then do some further screening for distance. More specifically, if we take some proto-matrices that originally had all of the cyclic permutations, we can design them such that the bottom rows, if we look at the permutation, the bottom rows have some non-orthogonal nature, such that when we remove the last 3 rows, we have enough degrees of freedom to design them essentially along this one diagonal, such that some of the elements are allowed to be non-commuting, and then the other ones are commuting. So essentially, everything outside of this diagonal has to be commuting, but that still leaves enough degree of freedom for some of them to not be commuting, and therefore allow one to have a distance that goes beyond the check weight. This, of course, constrains the choice of LPMs, so one can do a search across this constrained subspace. So as Kenta mentioned in his previous talk, one can have these in his original paper, he was looking at a block length of around 9,000 with, as designed, a rate just a little bit above 1/2. It's actually 1/2 plus 4 logicals coming from redundancies in the checks. It has data qubit degree 6, so each data qubit touches 3 X checks and 3 Z checks, and then check qubit degree 12. This is actually quite nice, right? Because 12 is a factor of 2 of 6. So it's also nice for designing circuits. And what he showed is that under a code capacity depolarizing noise model, you can get to 10 to the minus 8 block error rate at 4%, which is quite good if you compare against many other instantiations. So the key questions that we were interested in is, okay, this is like a large block length construction. How far can one bring it down? Is it intrinsic that you have to use these large block lengths, or can you take the same construction, look at practically relevant sizes, and still get good performance? And in particular, in practice, we care about circuit level performance, right? This is compared to maybe the bivariate bicycle code, this is a larger check weight. It's check weight 12 here. Is that a problem? Can it be implemented on hardware? We had these generic affine permutation matrices that you might think might be a little bit less native to the hardware implementation. So can we really take all of the ingredients here and make them suitable for a practical implementation in the regimes that we believe are important? Okay. So next, I'll tell you a little bit about how we actually take these and think about their concrete implementation. So the system that we'll be primarily considering is this dynamically reconfigurable neutral atom architecture that has gained a lot of attention in the last few years. The basic idea here is that you have qubits encoded in long-lived atomic states. People can now perform fairly high-fidelity gates by shining lasers on the system. So the way you program the system is that you move these qubits around using the optical tools. The nice thing is that a lot of optical tools have high levels of parallel multiplexing, which means that when you move them, you can move a lot of things in parallel. By shining laser illumination on the gates, you can then perform 2-qubit gates, single-qubit gates on the system. And just as a simple example of some of the very early demonstrations from Harvard, you have these qubits that are moving around in a torus connectivity in this particular case. So you see that there's a lot of flexibility in programming and designing this system. One of the key features of this is that we want to design it in a way that has a lot of control parallelism and reconfigurability. So this is just an example experiment that I was involved in which we performed logical magic state distillation. So each of the rows that you see here is a logical qubit. What you saw here is the encoding circuit that is performed in parallel across all 5 logical qubits. And then after you do the encoding circuit, you do parallel rows in order to perform transversal gates for the distillation circuit. So you can already see here that making them well suited, a large part of the design problem is how can we design in parallelism in the control and make use of the reconfigurability of the system in a very native way. When thinking about implementation of quantum LDPC codes, these are not a given. For example, this is, I guess, at this point, quite a few years ago that I generated, asking the kind of the frontier AI model at the time to generate a quantum computer based on high-rate quantum codes. And you see that it might have these like twisty, turny structures, which might not be very native for a hardware implementation, right? And so having arbitrary connectivity may not be hardware efficient. Of course, we always strive to develop better optical tools, but it's usually better if you can design it in a way that's well matched to the constraints of the system. If you think about the movie that I was showing you earlier, the natural constraint in neutral atoms, at least in the current generation of control tools, is this row-column constraint, where you're moving a grid of qubits at a time. Native operations would be things like translation or rescaling of a 2D grid, while making sure that the rows and columns don't cross when you're implementing this. So this is something that it's maybe not so clear at the beginning whether you take a generic code, you can implement it or not. But quantum codes are often designed with more structure. For example, if you look at these bivariate bicycle codes, there's translational structure. What we did a few years ago is to look at the product structure in hypergraph product codes or lifted product codes, where you naturally, in the code construction, in order to satisfy the CSS constraint, you want to have some product structure. And actually, the same type of product structure in these codes also matches well with the optical tools, such that you can have hardware-efficient implementations. In this particular proposal at the time, we had a reasonably efficient implementation with log L depth, where L is the size of the classical code, which is kind of one dimension of the system. But if you take the generic algorithm, it's kind of a tailored sorting algorithm that does divide and conquer. If you look closely here, we're working on smaller and smaller subblocks and doing the sorting. The generic algorithm to do this for implementation still takes like 20 milliseconds or so to do one of these syndrome extraction rounds. And so this log L depth, even though nominally it's okay, it still is something that you would like to cut down further. When thinking about the implementation of Kenta's codes, we started looking at these structures and tried to design it in a way that's suitable for implementation. So the first thing to notice is that there's a block circulant structure here, right? You see that these diagonals all have the same operation. So that's, of course, something that you can very naturally do. You just shift across the system to obtain the movements for the blocks. But you still need to implement the inner further affine permutation, right? So essentially what we want to do to transition from one gate interaction into the next one is to undo the previous one, right? We do the inverse and then kind of match the ancillars to what they should be. So what we really care about is the transition affine permutation matrix. Affine permutation matrices are closed under composition, so you still get a new affine permutation. We want to make sure that this new affine permutation is something efficient to implement. So we actually came up with a general algorithm for performing any APM in log depth as well. This is something that takes some ideas from these previous ones, like these kind of sorting ideas along each of the dimensions. This is also in a 2D layout, so it's actually a little bit non-trivial, but we nonetheless show how to do it in the appendix of our paper. But log depth is, in practice, still not so nice, so we would like to have a constant depth implementation. So the key idea here is to organize these qubits and the arrangements by the orbits. So by orbits, what do I mean? If you take an element and you apply this affine permutation matrix, you can keep on applying it, right? And what this is doing is essentially the first qubit gets mapped to the second one gets mapped to the third one. So you kind of have this like cyclic chain of operations when you think about this particular ordering. So essentially, you take the action of this affine permutation matrix, you're choosing a good basis such that now the implementation breaks down into individual cycles. So just to illustrate this, if we look at the transition matrix, in a cycle ordering, you have this very nice cyclic structure, whereas in the standard ordering, it would look a lot more arbitrary and complex. So under this ordering, the implementation of a single affine permutation matrix becomes several simple cyclic shifts. Often the orbits also tend to have like several ones of similar size, so you can do it in a very nice overall pattern. But you want to do this for each of the APMs, right? So how do we guarantee that the orbits of one APM is the same as the other one? This is actually, if you think about it, it's a familiar idea in quantum mechanics, where if you have commuting operators, they share a common eigenbasis. So similarly, if we have commuting structure between these APMs, between these transition matrices, then we can have them have shared orbits as well. So we just need to make sure that the transition matrices themselves have the right types of commuting structure. Note that this does not conflict with the original non-commutation in the code. We're looking at the transition matrices here, and we're also asking them to only commute with a certain reference matrix, where between themselves they could still have certain non-commuting structures. So we follow this recipe. We also separate it into row and column factors because we're laying these out in 2D, and we push most of the non-commutation into the thinner row dimension. And so then modulo these factors, we're able to get good cycle orderings. There's also additional structures that we impose to ensure that the different rows have the same types of shifts. So with these types of constraints, we can then put it into a standard search procedure where we take some protographs, block sizes, girth constraints. We have a girth search with girth 6. And then we impose these structural constraints. We generate candidates, filter them based on the distance, further verify them based on simulation, and co-design instances of these codes that have good properties. We primarily focus here on a little bit smaller block lengths of around 1,000 to 2,000 qubits, corresponding to 500 to 1,000 logical qubits. And so here are the code instances that we primarily focus on in the paper. We actually also found some with a little bit better parameters later on, but kind of overall the performance is roughly in this regime. So with 1,000 physical qubits, again, all of these are rate 1/2. We can have distance 12, and it decomposes into 3 length 32 orbits. So it's a very nice layout with 3 by 32 in each block, and then you have 12 blocks. So the dimension is actually kind of 36 by 32 in total. For the larger code, similarly, we can decompose it into 6 length 32 qubits with 2,300 physical qubits, rate roughly 1/2. We also find larger instances. For example, if you go to 4,600 physical qubits, then you can find instances with distance 22. So the question is, how well do these perform in syndrome extraction, right? So we can explicitly lay things out based on the atom movement schedule that we described, and actually just calculate the movement times based on the distances and the experimentally demonstrated timescales. So with 2 or 4 AODs, we get to something maybe between 8 to 10 milliseconds for these code instances. You actually see that doubling the size doesn't change the time too much. This is because of the particular way the shifts are done and the layouts. The horizontal dimension remains more or less the same between these two cases.
Time is for entire syndrome extraction.
Yeah, one syndrome extraction round. Yeah. You can also try to use bell checks or a shortcut to adiabaticity schedules, which we estimate would bring this down to the 2 to 4 millisecond range. Okay. So we've seen that these could potentially be implemented, but we would, oh, yeah. Yeah, so essentially some parts of it, you can parallelize them now if you have 4. So there are some parts that are parallelizable and some parts that are less parallelizable. And that's why you get an improvement that's almost a factor of 2, but not quite. I would say that this number 4 is like maybe 4, maybe slightly higher than this is a pretty natural number here. Because if you, like at some point, you'll be limited by the distance that you need to traverse in a given step. And at some point, that will limit you. You get pretty close to that limit when you're with 4 AODs. Yeah. Okay. So in order to so we've seen the construction, but we would also like to make sure that in practice, we can actually get very good physical performance. And in order to really benchmark this, we need fast and accurate decoders. Accurate, obviously, because we want to get good logical error rates, but fast is actually also crucial because otherwise, how are you going to probe an error rate that's like 10 to the minus 8 or 9, right? It would be impossible to do if you didn't have a decoder that was at least like somewhat modest in its speed. The goal here is to really assess the logical performance at the target scale and physical error rates. And we want to have the decoders be accurate enough to sample them, sample many shots. Oftentimes, people use various extrapolation methods. For example, there's this nice paper from Michael Beveland and others trying to use a bunch of techniques together. We often see various extrapolation techniques. But many times, it's a little bit hard to know whether you can fully trust that extrapolation. Sometimes there are trapping sets or error floors that you don't really see until you get to the very low physical error rate regime. And so I think it's very important to be able to directly benchmark this. And if possible, one should avoid extrapolation if you can. So we wanted to be as rigorous as possible here and directly characterize the error, not trying to base any estimates off of any extrapolation. And so what we did was to basically directly really simulate this and try to sample error events. If we think about decoding and think about the challenge of it, there's this very natural Pareto frontier of performance that you can have. You can have some decoders that are very fast but are not so accurate. For example, belief propagation is a very popular one. You can enhance belief propagation to be more accurate at the cost of high computational cost. Relay BP is a good example of this. And then finally, you can also just throw a lot of compute at it using a slow integer programming decoder that's much more accurate, but maybe takes a long time. So what we would like to do is to sit at a better point on this Pareto frontier. And the key observation is that the difficulty of decoding a given shot is actually dependent on the noise realization. If you're looking at a noise instance that didn't have that much noise drawn for it, then you can probably decode it with a relatively simple, fast decoder. Whereas for a harder noise instance, it will be much harder for this simple decoder to address. So there's actually an additional axis that one should be thinking about on this earlier plot, right? You have the speed accuracy trade-off, but actually the speed accuracy trade-off also is dependent on the particular noise instance. And it's really an instance-based property that you should be thinking about. So this motivated us to develop this hierarchical decoding method that after we finished and did some literature review, we found out that Nicolas Delfosse had also proposed something similar in specifically the surface code setting previously. So the idea is that you take a hierarchy of different decoders. Some of them are very fast, but don't converge as well. And then you pass it on to like a better and better decoder. So many of the easy shots are handled in the earlier fast stage. We tuned the parameters. We chose parameters for relay such that it was a good balance between the failures being still having relatively good convergence, but avoiding logical failures. And so in the regimes, especially for the larger code that we looked at, essentially all of the failures of the first two stages come from non-convergence, right? So your decoder just didn't converge. And because your decoder didn't converge, then you know that it was wrong. Whereas if it had a silent failure, then it would be harder to screen out, right? So we use the first two stages like this. And then the remaining failures, we feed it into a mixed integer programming decoder that handles the rest of the cases. We find that for this particular code, at this, all of these simulations that I'm showing for the circuit level are at 0.1% physical error rate of the circuit under an error model with no idling noise, motivated by platforms with long coherence times. We see that this large stage is very important to get good performance.
So what is roughly the time scale for the classical decoding for each of the steps?
Yeah, so we have a more detailed benchmark of the numbers in the appendix of the paper. I think with 32 rounds circuit level, I think the fast BP was maybe a bit less than a second. This is all CPU. Relay, I think, was on average a few hundred seconds. And then for 32 rounds again. Yeah, maybe I think average was maybe, so I think it was like 3 seconds per round. So maybe it's like 100 seconds on average. And then
but we do decoding after doing it
D rounds.
D rounds.
Yeah,
right?
yeah. So the latency, if you use a CPU decoder directly did this, would be 100 seconds for relay in this case. Yeah. And then I think Roby, there was a pretty wide distribution. The longest shots needed hours.
Right.
Yeah.
So then, would it imply that for this, I mean, this is a great, but would it imply that for practical use of this kind of complicated code that requires this hierarchical architecture for mixed integer programming, I mean, we cannot.
Yeah.
We cannot tolerate that such a long decoding time. I mean, I think this, if it takes several hours,
Yeah.
probably even if we go to FPGA, whatever the most optimized version, it's going to take pretty long time.
Yeah, so I guess my perspective on that is I think there could be a world in which it's actually okay. The argument is the following. If you could get the earlier stages to converge well enough, right?
Yes.
Like let's say that the second tier, let's say that the first two tiers you can put on FPGA, that's super fast. It's like basically, let's say it's 1 millisecond.
Yes.
And let's say that you could get 6 nines of convergence. What that means is that if you occasionally needed to fall back to a mixed integer that took an hour, if you multiply 10 to the 6 by 1 millisecond, you get maybe 1,000 seconds. Okay, so maybe an hour is a little bit long, but if it's basically the point is if it's sufficiently rare, then you could actually potentially tolerate that.
But what you're showing is it's not sufficient.
Here it's not sufficiently rare. Yeah, so this is not like the particular parameters tuned here are not enough. But we basically like just took it mostly out of the box. Like here in this particular case, the circuit syndrome extraction schedule was just like the first one that we found. We didn't even optimize it. So I think there's room to gain from there. We also, in this case, didn't actually tune for the circuit level for various reasons, mostly that we forgot we didn't tune the relay parameters.
Oh, okay.
So
Sure.
I think it's like possible that you can get better than this. I still think that it remains to be desired to improve this more, but you could imagine there being a regime where it could work. Yeah.
Okay. What's the logical error rate for each step?
So the convergence rate is the
convergence that might trigger something.
yeah. So we don't see any logical errors on the converged shots. Yeah. So
Oh, so like that 5 times 10 to minus 9 is like no converging.
oh, so the mixed integer does always have a certified solution. So we run the mixed integer programming to certification, and then you look at the final logical coset that it gives you, and then there was one shot in 200 million that had a failure.
You don't really classify like which decoder gives that.
The first two, when they converge, they always are correct for the larger code. Again, this is for the larger code. These depend on parameter regimes that you're choosing. Yeah. So the first two in this regime, they always converge. And then, they always had the correct logical coset upon convergence. And then the last one had one failure. Okay. So the circuit level logical error performance that we see is for the smaller, like 1,000 qubit code, we saw 7 errors in 14 million shots. And these actually are limited by the earlier stages. So it's possible that if we further tuned, we could get even better performance. The larger code, we saw 1 error in, I guess it was 400 million shots. I mean, it did take quite a bit of cluster time as well. It's not just the decoder, but this still gives us fairly good evidence that these codes can actually be quite good. So the block error rate per round is around 1.5 times 10 to the minus 10 for this larger code. And then if you divide by the number of logical operators, as might be well motivated during a storage setting, then you're looking at 1.3 times 10 to the minus 13. So something that is in the ballpark of what you could potentially think about using in a large-scale algorithm. Yeah.
But there's no idling errors, so this doesn't take into account your more efficient sorting scheme that you worked out. I mean, that doesn't play a role here.
Correct. Yeah. Yeah.
What is the
Oh, yeah. So T3 only here means if you assumed that you could use like a slightly better tier 2 decoder, right? So then you would look not just at the non-converged shots, but also like you knew which shots failed on the second tier, and then you redecode them with this Gurobi like integer programming decoder, then that's the tier 3 only.
So actually, if you use the integer programming decoder for those fast converging cases of the BPD or relay BP decoder, does integer programming speed comparable to the relay BP or still very
It's still slower. Yeah.
Still very slow.
It's still slower than relay. Yeah. Yeah. It's actually not a huge gap, like because relay itself isn't super fast if you do a lot of legs, but it is still, I think it maybe is a factor of like 5 to 10. Yeah. Okay. So we can also look at the logical error landscape, and in this case, we decided to use a phenomenological error model instead. So simulate with data qubit noise and measurement noise. And you see this very clear characteristic behavior of a waterfall error and an error floor. The top two curves are this only up to relay. And then the bottom two curves are this combined decoder. Here we are counting failures in the earlier stage as a logical failure. And so the floor, kind of this lower slope that you see here is actually dominated by the first two tier failures, mostly I think the relay tier failure. In the waterfall area, you see that the error suppression is actually a lot faster than the distance would suggest. Like the effective distance, if you just fit the slope, is something like 30 or 40, mostly because in this regime, you're dominated by entropy factors. And so you have actually a steeper error suppression. And then afterwards, you have an error floor area. In this case, here the effective distance actually is less than 7, which we believe is mostly limited by like choices in the decoder. Okay, so another question that one can ask is,
one question. In order to reach like 10 to the minus 14, 13 error rate.
This is per logical per round. So the number of samples is, so you get a factor of 30 from the number of rounds, and then you get a factor of 1,000 from the number of logicals.
Okay.
So the sampling is around 10 to the minus 9.
I was just wondering how you could do the simulation.
Yeah.
Okay, so quick question. So in Professor Kasai's code, I think just DB gives a waterfall behavior, but here to see it, you need the mixed integer programming, right?
Yeah.
Is that because like this is a phenomenological error model and it has like syndrome?
I think so. Yeah.
Errors, or like even if you just like consider code capacity, you don't see any waterfall behavior.
You do see waterfall behavior if you simulate code capacity for these. It's of course not as sharp because it's a smaller code, but you do see the right shape. Yeah.
So like if you consider like errors or like those like syndrome extraction errors, that kind of prevents you from seeing waterfall behavior just using BP.
I think so. Yeah, I mean, maybe I wouldn't say prevent, maybe, because if you look at it, right, you are still steeper. It's just that the waterfall is less good. Yeah. Okay. So another natural question that one might wonder is how good are these codes? Like, what parameters should we actually expect to achieve? And here there's a very natural trade-off between the block length that you have and the achievable encoding rate. What do I mean here? If one looks at the classical coding theory literature, there's this pretty famous paper from Polyansky and others in which they obtained finite block length estimates for the achievable parameters and try to say, okay, for a given block length, what is actually, for a given block length, for a given logical error rate, what rate can I actually achieve? And those actually on the classical coding side turn out to be surprisingly tight, even for a few hundred block lengths. So the basic idea of this, which we adapted to the quantum setting, is the following. In the waterfall regime, you have high entropic contribution, meaning you have a lot of different contributions from various types of errors that could occur. And so heuristically, with the central limit theorem, you'll get like a normal distribution. And so the logical error rate shape will look something like a normal distribution. The achievable rate at a finite length will have the following contributions. The first one is what you would expect just from the hashing bound. So this is like information transmission for a given error rate, what rate of information transmission I can have. And then there's a finite size correction that comes from the variance of the entropy. Roughly, you can think of this as each time I'm drawing a noise realization. And when I draw this noise realization, this particular sample that I'm drawing won't necessarily have the entropy of like the average case. So there will be some variance. And we can characterize that variance. We can characterize how far it was from like this average entropy for the given actual sample by using a variance. And then we can then plug that in with a tail to see like whether our actual sample was kind of within or outside this hashing bound for this particular sample. So you can take this and you can compare for varying block lengths what the bound heuristically adapted to the quantum case gives you, and what the actual codes achieve under decoding. So this is still using a hierarchical decoder, but actually Gurobi was time limited, so a lot of them actually are not going to convergence. And I'm comparing here the depolarizing error rate that you need to put in to achieve a target logical error rate against this like heuristic bound. I should say it's more a heuristic estimate rather than a bound, because like as with the hashing bound, it's actually not an actual bound, right, for quantum codes. And so you can see that the overall trend is matching. The concrete numbers actually have still about a factor of 2 gap. We don't have a very good sense, but my inclination is that this is likely the bound could potentially be tightened because we're imposing things like LDPC constraints and whatnot. But this is something that is maybe still a little bit open as to whether it's a code improvement or whether the bound. But we can also try to compare across different code families. So here, what I'm taking is the same type of bound as earlier, putting in just very heuristically a depolarizing rate of 0.03 and a target error rate of 10 to the minus 9 per logical or 10 to the minus 12 per logical, and then comparing against what the bounds should give you for these finite block lengths. Again, these curves, like the curves themselves, are depolarizing noise, right? So these are not bounds at all, but they hopefully give you a heuristic sense of what to expect. And you can see that in this area of like different block lengths and different encoding rates. So on the bottom left, like I guess earlier encoding rates were a lot lower, right? Less than 10%. And so they're all kind of in this bottom left regime. But what we're able to achieve here is something that actually looks reasonably close to this overall Pareto frontier if you just kind of look at the lines here. Yeah, so I think this is quite good evidence that these codes are at least in a pretty good regime in terms of where they are for their numbers. Small improvements might likely still be possible, and I'm sure there's a lot of more detailed adaptations, but I think it's likely that this is roughly the parameter that you should expect in these block length regimes. Okay, so in summary, I've told you about how we can take these nice new constructions and really understand how they can be practically implemented, as well as done at a very good circuit level logical performance. Of course, we're also interested in further extending these, performing logical gate operations, developing better decoders, since these last fallbacks are still a little bit undesirable at the moment. For logical gates, I'll just advertise this previous paper that we wrote with Qian and Nishad, as well as other collaborators, trying to design logical gates with parallel structure as a motif for designing improved space-time overhead for logical gates. And with that, I'd like to thank my collaborators, particularly Qian and Nishad, who were together driving a lot of the results that I showed today.
Any questions?
For logical operation, I think you mentioned you're gonna use the Butt syndrome extraction protocol, but if you're gonna do surgery, maybe it's desirable you know how logical operators are given in this memory code. And I think Oratomic mentions that in their paper, like for LP code, you can write down maybe some of the logical operators. I don't know, but can you say anything about this Kasai's code?
Yeah, that's a great question. Certainly, writing down a good logical basis is non-trivial for these larger blocks. Even though there is some cyclic structure in the code construction itself, it so far hasn't been clear how that generalizes to the logical basis. What we've been able to find is maybe logical bases of weights like maybe around like 100 or so, a little bit less than that maybe. So it's still a little bit higher weight than one would want. But indeed, that's an important thing to see if there's like better constructions that one can get. Yeah.
Thank you.
No more questions?
Yeah, that was a question. So Harry, in this kind of decoding thing where you pass to like more costly decoders, have you considered using post-selection at some point for like rare how fast that is?
Yeah, you can certainly do that. You can kind of post-select out failures at any level. You can also set a runtime bar at the Gurobi. Here, I think it was more a proof of principle of like what could be achieved. I think also for the memory, because we're using these as memory blocks in an actual computation, my feeling is that if ultimately you care about still the logical error rate as relevant to like implementation of a given time, right? So if you post-selected in that case, because it's the memory block, you kind of need to throw out the entire thing. So it's almost as if it was actually a logical error. So I think you might not be gaining too much from viewing it from that perspective. But yeah. Yeah, I think it's certainly in some region, especially if you're looking at, say, like a gadget on the side, then you could definitely use that. Yeah.
Yeah, just one question also regarding this hierarchical decoding. So yeah, what I really expect is that so near the threshold, basically what I would expect is that this BP and relay BP doesn't really do much, and mixed integer programming really does a lot of jobs, and it takes lots of time.
Yeah, so that's partly why for the circuit level simulation, we only simulated at 0.1% physical error rate, because if you go to very high physical error rate, then most of your shots are passed to integer programming, and it, as you said, becomes too slow. And also it's a harder problem for integer programming, right? So I think my perspective on that is that you actually, in practice, you don't care as much about the threshold, right? You care about, for your actual hardware system, what your logical error rate is going to be. So it's actually like, it's actually kind of a fortunate combination of regimes that in the regime you actually care about, this decoder actually has some reasonable chance of working.
But what I would expect is that for neutral atom system, we're more like close to the threshold.
I think if you're operating very close to the threshold of a given code, then I guess two things. You probably chose the wrong code because you should maybe chose a code with higher threshold such that you're not running into that. And second, like I think if you're in, let's say that you're in like 0.5% physical error rate regime in the long run, then probably your overhead is going to be large regardless of what code you're going to use. And so you should try to drive down the error rate. Yeah. Yeah. So I think it's true that the current error rates aren't quite in the regime that is needed. I think that's a problem that the hardware people need to solve for this to actually make sense.
So I think I've seen that like there's a convergence rate gets rapidly increasing to a larger value as you tune say a p equals like a 0.1 down. Like if you like, how should I say, if you decrease p like slightly, like BPOSD can also work much better.
Yeah.
Right? So the fact that around that tipping point, you have to rely on this hierarchical decoding that takes lots of time probably means that for a really practical quantum computer, you need a hardware noise to be actually not like 0.1%, but like maybe points like much smaller. Or for because thinking about
I think that's possible. Yeah.
say,
Yeah. I'm still somewhat optimistic that there's like room to improve in the decoding and the circuit construction. But in general, similar to my answer to the previous question, I do think that it's probably better if we can like push it just a little bit more down. Like I think maybe another comment to make is that people often say, oh, like decoding is kind of hard and whatnot. That depends hugely on the input error rate, right?
Yes.
Like if you had a 10 to the minus 4 physical error rate, then your decoding problem will be a lot easier. Yeah.
When you were when you were looking at the circuit level performance, did you ever check if the circuit level distance is maintained?
We didn't directly check, and yeah, I guess we didn't even optimize the syndrome extraction circuit here. It was just like the first one that we basically made, and we were like, oh, this looks okay. So we just like essentially by the time we were like, oh, maybe we should check it, we were about like 50 million shots in. And then we had like a very big sunken cost fallacy maybe. So that's why I think this likely can also be improved a little bit more. Yeah.
Thank you.
if no more questions,
I think there was one in the
Oh, yeah, I
back.
just wondered if those like told us.
Yeah, that's a good question. We didn't. Maybe there's also an interesting comment to make here. So we didn't explicitly check the single shot properties of this, so I don't know for sure. Yeah, like we didn't check confinement, if that's what you're asking. That being said, there's actually a very interesting phenomena that you see when using the relay decoding here that maybe partly also is related to some of the previous questions, which is even if it's not single shot, like you can still potentially use a windowed decoder and just see what happens, right? And we did actually try that in the earlier stages of the project. And what we saw is that actually the windowed performance is better than the full decoding performance. The interpretation is that most of the failures are non-convergence. So by choosing a smaller window at a time, you actually get better convergence. So I think based on that, even if it's not like technically single shot, it seems like in practice it actually might be okay-ish single shot. But we haven't done very exhaustive evaluation of this. So we don't fully know the answer.
okay, let's thank the speaker.